So this lecture is on momentum and impulse. This starts our momentum section of the energy and momentum unit. It is section 5.1 in your textbook. Now, this first slide talks about it shows a car crash with some Formula One race cars, and it says here that this driver in this car walks away from this crash without a scratch. And using some practical applications of Newton's laws of motion, engineers are able to design cars that can go very fast, but have safety equipment that can protect the driver from injury. You might have learned this in your grade 11 class about some applications of Newton's laws of motion, but we're going to look at this from a different perspective on what effect momentum and impulse have in terms of safety in car crashes, as well as a number of other applications. So momentum, when Newton originally formulated his laws of motion, he referred to what he called a quantity of motion. And that quantity of motion was mass times velocity. That term is now referred to as momentum. So momentum is the product of the mass and velocity of an object. So momentum is a vector quantity because the velocity is a vector and scalar is velocity is a vector. The mass is a scalar, but because we're multiplying a scalar by a vector, our momentum is a vector quantity. So direction is important for momentum problems, and momentum problems get a bit more difficult the more dimensions we start to introduce to those problems. But what I'd like you to do on the next slide, copy this down into your notes. This gives us this basically just explains the equation. It's really simple. It's just mass times velocity. Momentum doesn't have its own unit, so momentum is measured in the units kg meters per second. For this, for the lecture slides that you'll see here, they use the letter P for momentum, and I'll be using P or rho because in a lot of applications and textbooks, you'll see that they use rho, although rho looks very similar to P. If you look on the side there, that's a picture of what rho looks like, and it's very similar to P. It's a Greek letter. Lowercase rho is momentum, but oftentimes we just use a P. So if you hear me say rho or P, I'm referring to momentum. So here's a simple little problem here. It says that we have a hockey puck. It weighs 0.3 kilograms, and it is traveling across the ice at 5.6 meters per second north. So we multiply 0.3 times 5.6, we get 1.68. Rounding for significant figures, we get 1.7 kilogram meters per second north. Make sure you put the units in for these problems, even though they're not a particularly defined unit. It's important to label that because that way you will know, it'll make me know that you understand that momentum is a different quantity than force or velocity or energy. So what is impulse? Now, with Newton's first law, it says that the velocity of an object is constant unless it's acted on by an external force. So the net force applied to an object will, if it's unbalanced, the velocity of the object will change, which implies that the momentum would also change. So let's look at F equals ma, and a is the change in velocity over the change in time. So that can be written as Vf minus Vi. And then if we expand that m, we have m times Vf minus m times Vi. Anytime we have a mass times a velocity, what we're finding is a momentum. So our F equals ma ends up being F is equal to the change in momentum over the change in time. And if we isolate that for the change in momentum, we have delta rho equals F delta t. So that delta rho, that change in momentum, is what we call the impulse. So impulse is always written with a delta rho. It is Newton's seconds is how we can write that, but it's also the same as kilogram meters per second. Please copy this slide down. And again, impulse is a vector quantity, so direction does matter. It's important for these problems. So this question here says a golf club exerts a force of 5,300 newtons in the west direction on a golf ball. And it exerts this force over a time interval of 0.0054 seconds. So what's the impulse of this interaction? So we multiply the 5,300 times 0.0054 seconds. We get 28.62. Rounding for significant figures, we end up with 29 Newton seconds, and it's in the west direction. So that force that we said that was acted, it's hard to say that a force acts on an object at an instantaneous point in time. What actually happens is the force is exerted on the object over time. So a force time graph of that situation of the golf ball getting hit by a golf club would look something like this. We have at time 0 no force is applied. At about 5 milliseconds we end up with our maximum force, and then at 10 milliseconds our force goes down to 0. So there's a very short time when this force is applied. Now, another thing I'll quickly mention, if you look at that image of the golf ball, you can see that at its moment it's being hit, the golf ball itself has deformed. It's not totally spherical. It's been deformed because it's been hit with a great force over a very short period of time, so it's experienced a very strong impulse. That deformation is going to result in the golf ball shooting back to its original form, but you will see that that's partly what allows a golf ball to spring so much from getting hit by a golf club. So that milliseconds of contact of the golf club on the golf ball is going to cause a force that is great enough to increase the momentum of the golf ball. So before the hit, the golf ball had a momentum of 0 because its velocity was 0. After the hit, it will have a non-zero momentum, but it will also, the change in momentum that it experienced can be considered its impulse that it experienced over that short 10 millisecond period of time. So in later courses in physics in university, you'll be finding impulse by finding the area underneath the curve of a force time graph. For our purposes, what we are going to do is we're going to talk about average force over a time period. It makes the calculations a lot easier to solve, but just be aware that impulse calculations aren't typically as simple as just a force times a time. Now the impulse momentum theorem, please copy this slide down. Impulse, or delta rho, is equal to force times the change in time. This is equal to the mass times the change in velocity, or it's written as mass times the final velocity minus mass times the initial velocity. So that'll give us our impulse. So it's our change in momentum. Let's look at this problem here. We have a hockey puck. It is 0.16 kilograms. It's traveling 5 meters per second north, and a slap shot changes the puck's velocity to 40 meters per second south. It says that the collision lasts for 0.020 seconds. And we're asked to calculate the impulse imparted by the hockey stick and determine the average force applied to the stick by the stick to the puck. So here are our givens for this problem. One thing to note, our initial velocity is 5.0 meters per second north. Our final velocity is 40 meters per second south. So we have to keep in mind that this one's in the north direction, this is in the south direction when we're doing this calculation, and we'll have to be consistent when we're doing our math here. So our delta rho, our impulse, is equal to our m times Vf minus Vi, which is equal to m 0.16 times Vf, which is 40 in the south direction, minus Vi, which is 5 in the north direction. I cannot add or subtract north and south directions, so I have to change those signs, or those directions. So this is 40 south minus 5 north is the same as, or rather 5 north is the same as minus 5 south. So subtracting a negative 5 south would be the same as adding a 5 south. So this gets me to delta rho equals 0.16 times 45 south. And doing that quick calculation here, I get 45 times 0.16 gets me to 7.2 Newton seconds in the south direction. The second part of this asks what's the average force. So this is my first solution to the problem. Rho is equal to F delta T. So F is equal to the change in momentum over the change in time, which will be 7.2 over 0.002. So dividing this by 0.002 gets me to 3,600 newtons. Now, rho was in the south direction, so technically this is south, which means that this would also be in the south direction. That's my second question. That's the solution to my second question, the average force applied during that time interval. Here's another problem. It says a student practices her tennis volleys by hitting a ball against a wall. So the ball's mass is listed. It says it's traveling 50 meters per second west before hitting the wall. Then it bounces directly backward at 35 meters per second east. And this is pretty much the same as the previous problem. So I will let you try to work this out. Just be aware that 50 west that you see there, and 35 east, when you're subtracting those, they have to be in the same direction. So you'll have to switch the direction of one of them in order to get this this calculation correct. It's not just 50 minus 35 or 35 minus 50. You have to make sure you do that the proper way. And if you're having trouble, look back at the solution to the previous problem. So what does impulse have to do in terms of auto safety? So that force that we had calculated during those short time intervals, if we look at the equation, force equals the change in momentum over the change in time. Anytime we have, or basically our force is directly proportional to the impulse, and inversely proportional to the time of the crash. So because our force is inversely proportional to the change in time, and because we divide by a very small number, we get a large number. If we can increase that time, then we can decrease the force applied. It's kind of difficult to change the momentum because force is proportional to the momentum. But it's kind of difficult to change that momentum because of the fact that our mass of a vehicle, we could make the vehicles lighter. That's true, but there's a certain limit in terms of when we can make how light we can make a vehicle. And in terms of the velocity, we can try to encourage people to drive slower, but in a high impact crash, the velocity would be high as well. So the thought was, when we were making cars originally, was that if we had a really, really strong car, then the passengers inside would be safe. The problem with this is that with a strong car that wouldn't deform, we had incidents where the change in time, or the delta t, was very short for a moment of impact. This caused a very high impulse, which caused a high force, which caused our passengers to kind of bounce around in the car, and things like the backs of seats, the steering wheel, everything would hurt the drivers or the passengers inside the car. So in the 50s and 60s, they were later on, past the 50s and 60s, we started to create cars with crumple zones. And these crumple zones actually increase the moment of impact in a collision. By increasing the moment of impact, we end up decreasing the force applied to the passengers inside the car. This slide here just says kind of what I was saying previously. It says when a rigid car hits a wall, a huge force stops the car almost instantaneously. It says the car might not even look like it was only slightly damaged. However, parts of the car, such as the steering wheel, windshield, or dashboard, exert an equally large force on the passengers. So when a car with well-designed crumple zones hits a wall, the force of the wall on the car causes the front of the car to collapse over a longer time interval. So that, again, like I was saying, because we have a greater delta t, that force has to be smaller. So we use this concept for a number of things. Helmets, for example, they have that cushioning inside, which kind of increases the moment of impact of a collision or a hit from an object. So this slide I'd like you to copy down. So since our delta P is equal to F times delta T, and delta P does not change because we could make the mass smaller, we could encourage people to drive slower, but ultimately our momentum will be is something we cannot change in a collision. We can increase the time, and by increasing the time, we decrease the force. Applications of this are crumple zones, airbags, safety helmets, and sports equipment. So this question, I'm just going to read through this. It says that we have a bungee jumper, who jumps from a high tower. As he reaches the end, the bungee cord begins to stretch. The cord stretches for a relatively long period of time, and then it recoils, pulling him back. So after several bounces, he dangles unhurt from the bungee cord. So let's use the concept of impulse to explain the difference in the results of a jump using a proper bungee cord and a jump using an ordinary rope. Now, if he had an ordinary rope, once the rope became taut, there would be a strong force that he would experience that would be pulling him back towards the tension of the rope. With the bungee cord, as soon as it starts to stretch past its equilibrium point, it's increasing the time that the impulse is happening, and by increasing the time, we're decreasing the force of impact.